Hi there. In this video we're going to look at an optimization problem, and this problem involves maximizing the area of a square inscribed in a semicircle. I take that back, it's not a square, it's a rectangle. It's a rectangle inscribed in a semicircle. So you can see what I've done is I've constructed this rectangle so that as I move it, it stays inscribed and the area changes. Okay, I'm interested in where does this point have to be? In other words, what does this x value have to be in order to maximize the area? Well, if we were way out here, we can see that we have an area of 11.10 square centimeters. As I move it to the other extreme, I can see that it's 9, and somewhere in between is going to be at its biggest. And this looks like from the picture that that's going to occur right around here. Oops, there we go. So right around, I don't know why that says negative. Let's see. Here we go. That's better. Sorry about that. 3.55, somewhere in that vicinity, we're going to maximize that area. Okay, so this is just an approximation. It's not conclusive proof that that is. So let's go ahead now and try to figure this out analytically. All right, here's the same picture, only it's not as nice as the previous one, but it will do. And I have this rectangle inscribed in here. I'm interested in its area. So whenever you do an optimization problem, you always have to figure out what is a function, what's an equation, I guess, that's going to describe the thing you want to maximize. Well, how do you find the area of a rectangle? The area of any rectangle, if you think back to your geometry class, says take the length of that rectangle and multiply it by the height. Okay, well, what is this length? Well, if this is the origin, and this is just some random point somewhere in between 0 and 5, then we can just call this x. And this distance is going to be the same, so this length then is going to be 2x. Okay, so the length of my rectangle is 2x. Well, what is the height? Well, think about it. If this is x, then x gets sent to this semicircle up here. That's just f of x, or f of x, I guess, would really be this guy right here. So the height then is simply going to be the square root of 25 minus x squared. That's your height. Oops, square root. Sorry. Minus x squared. I apologize for my handwriting. Okay, so here we go. We have an equation that describes the area, the thing that we want to maximize, in terms of a single variable x. And a lot of times in optimization problems, sometimes you'll get other variables that creep into here. It's at that point that you would need to find a secondary equation to help you eliminate that. But this doesn't have any other variables, so we're all ready to go further with it. Now, just to drive this point home a little bit further, if I were to graph this thing, if I were to graph this function right here, you'll notice something. You'll notice that we get this nice smooth curve. Now, don't worry about this stuff over here. Okay, we're only interested in x values in between 0 and 5. That's kind of like our feasible domain. Okay, x can take on other values over here, but they don't add anything to our problem. So our reasonable domain is from 0 to 5. And you can see that if x is right around this area right here, that's going to produce an area of right around 25. So how do I find this point using calculus? Well, I want to find the derivative and set it equal to 0 because the tangent line here, the slope of it is equal to 0. So let's do this. Okay, if I differentiate, I get dA over dx equals. Now, we have to use product rule here. Product rule says take the derivative of your first function and multiply it by your second function. Okay, this is product rule. Plus the derivative of your second function. Now, this is going to get a little messy. Not too bad, but here's my second function, and I want to take the derivative of that thing. So it will be 1/2 times the quantity of 25 minus x squared raised to the negative 1/2. Okay, now we have to use a little bit of chain rule. Chain rule just says go back inside into your inside function and take the derivative of that, and that will be negative 2x. So there's the derivative of your second function, and now we have to multiply it by our first function. Okay, there's your derivative. Now it's at this time I want to make note that the feasible domain, remember, for this thing is really from it's really from -5 to +5, but because you just kind of repeat, you just get a bunch of repeated areas. We could think of our area as our domain from 0 to 5. These are the ones that matter. Anything to the left of 0 just repeats all the areas that this will give us. Okay, so I want you to keep in mind that this is where our x value is roaming. Now, let's go ahead and simplify this very quickly. And I'm going to skip some of the algebra. I'll try to do as most of it as I can, but I don't want this video to be too long, and I don't want you to get hung up on the algebra. Okay, so what do we have? We have 2 times the square root of 25 minus x squared. And if you look very carefully at this, 1/2 times 2 is 1, and we're left with a negative 2x squared. And this is going to be over this. Okay, this is to the negative 1/2 power, so we can actually bring it downstairs, make it a positive 1/2 power, and I have the following. Okay, now what? This is our derivative. If we set this equal to 0, that will hopefully help us find that critical point that we were looking for earlier. Okay, in other words, it's going to help us find this critical point right here. We suspect there's a critical point right around 3 point something. Okay, so let's set it equal to 0, and at the exact same time that I'm setting it equal to 0, I'm going to take care of some of this mess up here. So if you multiply your entire equation by this denominator, okay, nice things are going to happen. Now, I always tell my students that the two things they're going to struggle with is the notation in calculus and the algebra. So if you need to put this over 1 to help you see what's going on here, that's fine. But if I multiply my entire equation by this thing, look what happens. Now remember, this is 0. I've already set this equal to 0, so this times 0 is just 0. And this multiplied by this guy, well, the square roots are just going to more or less cancel each other out, if you want to think of it that way. And I'm left with just this. And look what nice thing happens when I multiply these two together. Your square roots cancel all together, and you're left just with a minus 2x squared. Okay, so now if you look very carefully at this, this doesn't take too long to see that it's going to factor to 0 equals 50 minus 4x squared. Okay, and let me get myself just a little bit more room here. Now I want to solve this, and I get negative 50 equals negative 4x squared. Divide both sides by negative 4, and I get x squared equals 25 over 2. Taking the square root of both sides, let's go up here now. Taking the square root of both sides, I get x equals 5 over root 2. Now, if this were an Algebra 2 class or something, I would make my students do this. I would say plus or minus, okay? But remember, the minus, our feasible domain, if you will, is just going to be from 0 to positive 5. So we really don't need the minus here, but it doesn't hurt to have it. So there's our two critical points. Really, only one critical point matters. And if you crunch that on your calculator, you should get something right in the vicinity of 3.5. I can't remember. I think it's 3.54 is the critical point. Okay, so we suspect that this is going to maximize our area. That is the x value that most likely is going to maximize our area. We only really need to do one last thing. Remember that feasible domain from 0 to 5. Okay, well, notice that this lives in there. And we had an extreme value theorem several videos ago that said that if you have a continuous function going through an interval, that the extreme values are either going to occur at, whoops, I shouldn't do F, let's do A. They're either going to occur at the endpoints, okay, or at the critical points. So really what I need to do, just to make sure, even though we really know that this thing is the answer, is we need to test these things in our area function, in our original area function. And the smallest value is going to be a minimum, and the largest value is going to be your maximum. Well, if you substitute 0 back into your original area function, here's your original area function right here. If you substitute 0 in for that, you're going to get 0. And if you substitute this in for x, you're going to get 25. And then finally, if you substitute 5 in for x, you're going to get 0 again. So clearly 25 is the biggest value. So 5 over radical 2 maximizes the area. And that area is 25. I hope that made sense to you. We'll see you around in the next video.